Hello everybody, my name is Emilios and today we're going to be talking about performance analysis on HPX. HPX is designed to enable applications to harness the full potential of modern parallel hardware, from multi-core systems to large-scale distributed memory architectures. Its core philosophy is to expose massive fine-grained parallelism through lightweight tasks and features, allowing for efficient execution and latency hiding. However, writing concurrent and parallel application is only the first step. To ensure your HPX application is truly performing as intended, achieving maximum speedup and utilizing hardware efficiently, you must engage in rigorous performance analysis. There are various tools with which you can profile an HPX application, one of which is Intel's VTune Profiler. Intel VTune Profiler is a sophisticated performance analysis tool that goes deep into the execution of your code, providing detailed insights by utilizing hardware event-based sampling on Intel processors. For complex asynchronous runtimes like HPX, VTune is crucial because it allows you to pinpoint true hotspots by identifying which functions the most CPU time down to the source line, regardless of whether that time was spent in HPX scheduler or your application logic. It can also analyze microarchitecture efficiency by determining if your lightweight HPX tasks are suffering from poor cache utilization, memory stalls, or inefficient instruction execution. Issues often invisible to software-only profilers. And also visualize threading behavior by using the timeline to see when HPX worker threads are actively computing versus when they are stalled on synchronization, logs and waits, or idling, directly exposing concurrency and load imbalance problems. Building HPX and your application that uses it with Intel VTune Profiler compatibility requires you to take specific steps during the configuration and compilation phases using CMake. To ensure a productive profiling session with Intel VTune Profiler, you must build both the HPX library and your application in a configuration that provides the necessary debugging and simple information while still retaining optimizations. A crucial step is setting the appropriate build type in CMake. We recommend using rel with deb-info. This build type includes optimization flags for realistic performance measurements, but crucially it also includes the necessary debug symbols. Because Intel Trace Collector and Analyzer and VTune's API use the instrumentation and tracing technology ITT API to insert user-defined events, you should enable it by using the flag HPX with ITT notify equals true. You should also use the flag amplify root to pinpoint to the directory where VTune is. One last note is that if you want to work with VTune, you have to disable Apex. So let's now see a practical implementation of VTune. We have this script called sort. It's a simple program that generates a list of 50,000 random integers, then sorts them. So before profiling with VTune, let's run the script and see how much time it takes to run. As you can see, it took the program 4.95 seconds to run, almost 5 seconds, with 4 threads. Now let's run the exact same program, but this time under VTune's Hotspots collector, in order to find any possible bottlenecks that slows our program down. I'll type VTune collect-hotspots, result-dir and the name of the directory where I want to store the results of the profiling and the name of the script. VTune takes some time to run, so let's fast forward. Now that it's finished, we can open the report in VTune's graphical interface by typing VTune GUI and the name of the directory. VTune also provides the report in the command line, but in order to have a more detailed look, let's see the graphical interface. Let's look immediately at the elapsed time shown in the top left corner. The value for 46.7 seconds is alarmingly high for sorting a dataset of that size. In a properly optimized parallel scenario, we would expect this operation to complete very fast. This high latency is our first indicator that the parallelization strategy is ineffective. To understand why parallelism is so slow, we look at the top tasks section at the bottom of the screen. This provides the smoking gun for our performance issues. The task name to do work chunk has a task count of over 766,386. This reveals a severe granularity problem known as over-decomposition. The algorithm is launching a parallel region inside every single iteration of the short loop. Consequently, the runtime is flooding the scheduler with over 760,000 microscopic tasks. The average task time is listed as 0 seconds, which confirms that the time spent managing the life cycle of these tasks, creating, scheduling, and destroying them, far exceeds the time spent actually to do the work. We are essentially forcing the runtime to spend all its energy on logistics rather than computation. Finally, looking at the top hotspots list in the center gives us a breakdown of where the CPU cycles were actually consumed. The primary lambda function, which contains the sorting logic, accounts for only 31% of the total CPU time. In an efficient program, this should be the dominant consumer of resources. Instead, we see significant wasted effort. The standard vector operator takes up 20.3% of the time, and memory operations like standard move and standard swap consume another 70%. This profile indicates that the CPU is overwhelmed by memory access overhead and the constant context switching required to handle hundreds of thousands of tiny tasks. The system is thrashing moving data and managing threads, rather than sorting the array. So we're going to move to the timeline tab to see exactly what happens with the threads. So instead of you seeing a solid continuous blocks of green, which would indicate uninterrupted work, we see a fragmented pattern in the active thread regions, here at the top right. The timeline bars for the worker threads show a mix of green running segments interrupted by spin and overhead states. This fragmentation usually visually represents the stop-and-go nature of the execution. A thread picks up a tiny task, executes it instantly, and then enters a wait state or overhead state to retrieve the next one. The massive gap in the middle of the timeline further highlights the idle time, where the system was likely waiting on the main thread or serial portions of the code, reinforcing the conclusion that our granular task management has destroyed any potential for sustained parallel speedup. To further inspect our run, I'm going to switch to the platform tab and I'm going to zoom in. This specific view offers irrefutable visual proof of the granularity problem. What we see here is not a solid block of continuous work, but rather a dense barcode pattern. In this tiny time window, we can count dozens of distinct microscopic blue blocks on each thread. This blocks represents the individual HPX tasks that our naive algorithm created. The sheer density of these blocks visually represents the 766,000 tasks we identified earlier. Crucially, pay attention to the relationship between the brown CPU time bar at the top and the green running bars at the bottom. The brown bar appears solid, implying the CPU is 100% busy. However, this is misleading. The CPU is busy managing the timeline, not computing the sort. The tiny vertical white gaps between the colored blocks represents the scheduler intervening, saving state, context switching, and loading the next tiny task. This visual patterns is the computational equivalent of stop-and-go traffic. We are driving the CPU at full throttle, but we are forced to stop every few milliseconds to see its task. This explains why our elapsed time is 46 seconds instead of milliseconds. We are burning fuel on overhead rather than forward motion. So this was the performance analysis by VTune. Next week, we're going to talk about Traveler. Till then, happy coding, everybody.